Alright, yeah, I'll start us off with some prayer. Dear God, thank you for this day and for bringing us here today. Pray that so it'll just be an enlightening time for all of us, and we'll learn some interesting things. Pray that you'll help me to have clear thoughts and to explain things well. In Jesus' name I pray. Amen.
Amen.
Right.
Nathan has intrigued me with tales of the chapter we're skipping. He says there are interesting things in there. Yeah. Actually, did we skip that chapter yet? Or is it?
I think we're officially skipping that chapter now.
Oh, okay.
Yeah.
So,
Whoops. Alright, so here we're looking at homotopy groups, or hopefully we'll be getting there. Basically the idea for this is to kind of construct more of the, we have like the fundamental group, pi 1 of x, comma x naught, which is be viewed as like maps from s1, comma 1 to into x, comma x naught, and so we're going to generalize this for n being integers or positive or non-negative integers, where it's going to end up being pi n of x, comma x naught. Same thing with but from Sn, comma 1, or Sn, comma the base point in it to x, comma x naught. So that's kind of where we're headed in this. But I guess we'll start off with some definitions to kind of get into that. I'll start us off by saying
we're in chapter 11.
Chapter 11, yeah.
Homotopy groups.
Homotopy groups. We're going to be looking at function spaces. I'll preface this by saying I'm not absolutely as confident in this chapter as I have previously been, so hopefully it'll be coherent. Wire spaces, topological spaces. We define x, y, I don't know how you could say it, x to the power of y. So it's a set of all continuous functions from y to x. And it's given a certain topology, compact open topology.
Ignore it.
Is the help session going to be recorded?
Yeah. Yeah.
Okay. I couldn't figure out the last problem.
Oh, well, I posted the help session from earlier this week, but that's just was about solutions I've already worked out.
Okay.
See you, brother.
Okay, so it's going to be some basis of this topology is going to be consisting of all sets K, U, where K is a compact subset of Y, and U is an open subset of U. Of X. And K, colon U, semicolon is equal to such that f of K is a subset of U. Okay, and so since that's a basis, we can construct other open sets from that. And then we have this other definition, the associate of a certain function. F maps from Z cross Y into X. And its associate hashtag. True or right is here, let's see. Which maps from Z to the space of functions from Y to X.
It says the compact open topology on these functions for any space Y is precisely the topology given by uniform convergence on compact subsets. Hmm.
So, this f cosine Z is going to be a new function, which maps from Y to Z, where fz of y is equal to f of zy. Can we also have this evaluation map? E from functions from y to x, which, to my understanding, these aren't necessarily continuous. Across y to x by defined by e of f comma y is equal to f of y. Okay, pretty simple. And we get a theorem that about these associate and evaluation maps. So if we consider everything I talked about before, X and Z topological spaces, X for the Y, I'll just say that. With the compact open topology, then we have the evaluation map. Continuous. And f is continuous if and only if each of its associates is continuous. Or its associate function, sorry, is continuous. Okay, I'm not going to prove this. It's pretty straightforward, I think. Let's see. All right. Don't think the corollary 11.2 is super important, but if we come to need it later, we'll go to it. But here we're getting to what we call group objects and also co-group objects. Next section. So definition.
That is really like the sharp map in the musical morphism, you know?
Mm-hmm. Yeah, isn't the sharp map kind of like if it were like onto R into R instead?
Right, and C and Y are the same space,
Yeah.
but
It's also what I actually was going to have in my talk yesterday after I gutted half of it. It's called currying in functional programming, also known as in category the exponential transpose.
yeah, I know the law of exponents is more categorical than you might expect. When I was doing topology with when I was an observer to the topology being done between Dr. Mavinga and Spencer, they work in Willard's book, and there's something on exponentials in there that's just very general. That's a general topology book. It's like, need to get you a better marker.
Maybe I'm just not pressing. There we go. All right, we're back at it.
Oh, yeah. Huh. This stuff is like early in Willard's book.
Okay, so we have this thing called an initial object and a terminal object. The initial object has a unique morphism that maps it to each set, or each element, each other object, and the terminal object has a unique morphism that maps it. It maps each other object to it. So, got some examples. So in category sets, the initial object is the empty set, and the singleton set is a terminal object. Because there's only one, it's only one function that'll map the empty set to any set. It's just like, well, it maps everything to empty set, I think. And there's only one function that'll map something to a point, and that's just the function that maps everything to a point. Let's see. Category of non-empty sets has no initial object, so it has to be the empty set.
Where are you?
I'm on 315.
Aha, you got ahead of me.
And in groups, the group of order 1 is a zero object. Oh wait, what's it? Okay, I guess I should talk about what a zero object is. Just reading this. So if we have the pointed set star, which is pointed sets, if we have a singleton, star, then A is, so this is an initial object. Oh, and it's also a terminal object. If it's both initial and terminal, or yeah, if it's both initial and terminal, then it's called a zero object. And then in groups, the group order 1 is a zero object. Okay. Then we talk about the product object, which is pretty natural. Oh, not this one. Just so this way, if you don't mind.
Go for it. Huh. What does this have to do with homotopy groups? I mean,
Everything.
everything.
We'll go there, I guess. So if C1 and C2 in a category, or objects in a category, then I'm not sure if that's the proper notation, but that's what I mean when I say that. Their product C1 cross C2 with morphisms PI, as either 1 or 2 that map, C1 cross C2 to CI, to one of them, called projections. Pretty much what we have anytime we have a, so yeah, I see it. Probably know what it is in in groups or in topological spaces. And for every object X, there are also morphisms qi from x to ci, where, oh wait, there exists a unique morphism. Beta x to c1 cross c2. Making the following diagram commute.
Hmm.
So we have c1 cross c2. c1. p2. We also have x. q1. And so theta is equal to q1 comma q2. Okay, and then we also have the coproduct, which is very similar. I won't write everything. I might draw the diagram for that because it's actually pretty analogous to it. We have these other morphisms that are kind of like, they're called injections. So we have C1 coproduct C2.
So what's the theta map in the category in the case of sets? I mean, it's like,
Okay.
in the case of sets, the products are the usual Cartesian products equipped with the usual projections onto factors. You know, X maps to.
Okay, yeah. And so if the C1 and the C2 are both the original, are both the same set, then it basically just gives you the same thing twice, I think.
Oh. Huh.
Yeah, so the diagonal maps X to X comma X in the product set.
So the diagonal map is a particular case of this contraption.
Mm-hmm. Yeah.
Hmm.
Kind of a boring one in this case.
Yeah.
So here we have these injections and X. So everything's going the other way.
Oh.
And we have this.
Oh, I understand now. So we're looking at functions from X to like a C1 and C2. So if you can make a function to C1 and you can get a function to C2, of course you can make it yet another function to the Cartesian product of C1 and C2, this theta map, such that when you project that theta map with P1, you get back the C1, the Q1 function, or if you project back the... That makes sense. Never mind.
We have a
Just struggling to understand what on earth he's saying.
yeah. Same. Let's see. And so we have in the category of sets, we also have a similar one where it's a codiagonal. Okay, and then have a theorem that tells us some things about these products. This is 11.3. So we have C1, C2 in a category. C1 cross C2 exists. Then for every object X, there's a natural bijection. We have homomorphism morphisms from x C1 cross same one x C2 is reduction with x C1 cross C2. Pretty much the same thing when we're talking about the co-product. So do the same thing, but with this instead. Okay, I'm not gonna prove that one either. Alright, and then we're gonna define group objects. We have C category. Having finite products. Or okay, having products. And the terminal object Z. Then a group object in C is an object G. Let's see, and paired with the morphisms mu from G cross G. G you can guess is the multiplication eta from G to G, which becomes the inverse, and epsilon from Z to G, which is the identity, I think. With the following diagrams that commute. So we got a few here. Okay, one, we have associativity. So we have G cross G, mapping identity cross multiplication. Okay, sorry. G cross G. Here we have A cross Y. G cross G. So really it's just saying if we multiply the right ones first and then and then with the one on the left, it's the same thing as if we multiply the left ones first and the one on the right. Which is associativity, I guess. Identity.
Huh.
Where lambda and 1 are equivalences. So this is like the identity for the
So is a group object?
A group is a group object in the category of sets.
Okay.
makes sense. Okay. And we have inverses. We have G, and then if we take 1 from eta, we just get everything there. Where omega is the unique morphism of the terminal object. And so, yeah, but it gives you an identity. We have a similar case for the called the code group object, which you guys can see in your book. I'm not going to copy all this stuff down,
Mm-hmm.
but it's kind of dual to it, or maybe it's exactly dual to it. talks about in the category of sets that is on page 320. We get a contravariant functor homomorphisms from G, or from this set to G as a mapping from the category from this object to G to this set's defined on morphisms G as okay, right, yeah, so this is a functor, I guess I should mention that, where yeah, so when you take this induced map, which maps from functions from y to G, and maps them to functions from x to G. By G star of f is equal to fg. And likewise, if we consider everything flipped, we'll have this lower star, f is equal to gf. And so this one is a contravariant functor, this one's a covariant functor. Okay, let's see. I think the 11.13 is, 11.4 is super important. So we'll move on here.
11.4 prime is kind of important.
Okay, we'll get to that one. Thank you, Nathan. Okay, so if we have C category with finite coproducts, this is pretty much the same thing as 11.4, but with coproducts, I think. And it has an initial object. Then an object G is a cogroup. And C, if and only if this mapping takes values in groups. In this case, the multiplication, so I'll call it Px. G to x cross distance from Px to distance from G to x given by G, where M is the coproduct, the co-multiplication function. That's what it's called. And FG is wait, no, sorry. is, okay, so we didn't. Yeah, 11.3 is the part that I kind of skipped over, but, which one's this? 11.3 number 1.
And essentially that morphism is just defining F on the first part of the coproduct and G on the second part of the coproduct, intuitively speaking.
Okay. Yeah, makes sense. Maybe I could. Oh, 1, 2. Okay, yeah, that makes sense. Alright. Alright, now we get to loop spaces and suspension, which is pretty useful for this one. So if we're considering the homotopy category as pointed spaces, H top star, we have this lemma. We have H top star has a terminal object and an initial object, even if it's a zero object. And finite product and coproduct. Which allows us to do to use the theorems that we just presented. Okay, I'm not going to prove that. So now we're looking at, now we're going to talk about H groups. Actually, I use it at work. So pointed space X naught is an H group if there exists maps that we talked about, mu, theta, the product and inverses, and the and pointed homotopies. So mu of identity cross on X cross the multiplication is homotopic to product of multiplication and cross identity, which corresponds with the associativity. Whether you do the product first on one side or the other doesn't change. And we also have mu of decomposed with J1 is topic to the identity, topic to
It's 4 o'clock.
where J1 and J2 are the ones that are the injections that we erase that one. That we defined before. They're like the corresponding, or they correspond with the projections.
Mm-hmm.
And so like J1 of X is equal to X naught. J2 of X is equal to X naught X. Okay. And we have the product of identity and the inverse.
See, hard to write those maps without the point, is the point. You know, having
Right.
that X not floating around allows you to write these sorts of formulas.
Where's Dave's constant map? Maps to X. Maps to X naught. Okay. And similarly, we have an H prime group, which is pretty much the same thing, but with the coproduct instead. So I'm not going to write that stuff down. And
So the next lemma gives you these natural relations
right,
from maps to the. So the Z wedge V, that's the. How's that read? Like the Z, the upside.
Where?
Excuse me. What is that?
I think it's wedge.
Join.
Join?
Join? Yeah.
I mean, that's what I would call it.
Okay, well, I'll define what that is.
Well, he calls it wedge.
Yeah, I think I'd call it wedge.
He said it's viewed as the subspace.
Yeah.
Wait, where does he say that?
That's right. It's right.
Oh, okay. Huh.
So it's X cross X union X.
That's weird. I would call this a wedge.
Yeah, me too.
Call what a wedge?
The
the other way.
and
Yeah.
symbol.
Well, can't always get what we want.
Probably also calls that wedge.
Probably.
Maybe he
He
calls
also
it wedge.
uses the same
Maybe he calls it-
notation for the universal morphism for products and coproducts, which I find annoying.
Ah.
I think in Awudi he uses brackets for the angle brackets for the coproduct.
Uh-huh. Hmm. Where are my homotopy groups at?
We're getting there. We're not too far. Once we have the loop spaces and the suspensions, I think we'll have what we need.
Okay. I'm impatient.
Yes.
Gots to have my homotopy groups.
I gave you a taste of it at the beginning. That should
Just a taste.
that should hold you over. So, definition.
For
Loop
sure.
space. Omega x comma x naught is a function space. So x naught I dot.
Ah.
So that's functions from
Right.
this to this. Okay, so I understand some mappings of loops onto this space, I think. Okay, then we have, and so this omega is a functor. From homotopy spaces to function spaces.
So then, like the function space is itself a pointed space, and he uses this omega naught as its base point, right?
Okay, yeah. Let's put that.
And he also mentions here it's topologized with the compact open topology.
Yeah,
Yeah.
which is what we're always doing when we're doing function spaces.
You gotta be careful. You don't want it to be too late to topologize. Solid open.
Okay, and then we also have this theorem, 11.9, is that if x, x naught is a point in space, then
I'm guessing the H is for homotopy. We don't know yet. The H is for Herbert. No.
is it for, are you talking about the capital H?
Yeah, like H group?
I think it's, well, it's associated with the H spaces, which are named after Hopf. So maybe
Ah.
fix that at some point pretty soon. So I'm not gonna prove it though, but we have everything we need if we define the multiplication to be the kind of extension thing that we had done a long time ago when we were talking about paths.
Yeah.
And the inverse, I think it's just the inverse path.
So the multiplication is just the adjoinment of, or whatever you want to say, the joining of paths and or concatenation of paths.
Right.
And yeah.
And we have a
And the constant path at x naught is the, I guess, the identity.
right. Okay, and we also have a corollary, which says that for any point in space X, the mappings from a certain. So if you remember what we had done a long time ago, so if we use this bracket notation. It's just, this is for the H top, but it's the same as if we said like X to Y. It's just mappings from one to the other. But this is a special notation for H top star, or H top, I guess H top star. Okay, and this is a, sorry, this is a contravariant. From H top star to groups. If Y is a point in space, and if half classes of this then the product is class of their concatenation. Okay, now we define the suspension. If C, Z naught is a point in space, the suspension of C sigma of C is the quotient space Z cross I mod Z cross I dot union Z naught cross I. Okay, and so this kind of harkens back to what we had done with cones, where like the cone of this space I think was like Z cross I mod Z cross 1, I think, something like that. And in this case, a double cone
And it's stupid that
is this one.
cone construction, the way it's described in Retland, gave me fits. I could not make sense of it. Nathan, you were asking me questions about it. I was like, I don't know.
Okay,
It
so
was
double cone is going to
very
be
frustrating to me. Like, I tried to work on it and I couldn't get anywhere. So,
I mean, they didn't really, I think the biggest issue was they didn't really describe quotient topology very well, which made it difficult to understand.
Alright, so double cone is when you modify this with both points that are both squished into one, or both parts that are squished into one. And then this one, suspension, is where we also, let's see, consider, so if you have a point in Z naught, Z, then all of this part, Z naught across I is going to be it's going to be identified. So it's going to be squished onto one point as well. Okay. So, and another theorem is that the suspension defines the functor from H sub star to H sub star. Okay. Yep. I'm not going to write all this out, but we have this concept of joint pairs. So if we have two different functors, we have a bijection. I'll write something down. So F from A to C, where A and C are categories, and G from C to A, I think. Are F comma G is a joint pair. If
Cool. Oh man.
we have a bijection.
It's really neat what's going on in this chapter. Like all of your favorite things from linear algebra or wherever. They've got some sort of categorical analog.
It's also a generalization of Galois connection.
Ooh. Know that. This is? Or
Adjoints, yeah.
oh, okay.
Where this is natural, and we have a diagram. Should I show it to the camera? I don't want to draw it all.
You go for it.
Where you have this following diagram, which shows that it's natural.
Copyright now. Fair use, I hope. I could argue fair use. Please don't sue us. We show it because we love it.
Yes. Okay, and then cool theorem is that the suspension and the loop space is in a joint pair. Could go through this proof if you guys want. It's not too long. It's up to you. You want to get to the?
You can go on.
Yeah, we'll go on.
Okay.
We'll get to the good stuff. Okay, then we also have the if. From that we have the if.
His comment under exercise 1117 is interesting. Exercise 1117 says if f and f comma g is in a joint pair, then f preserves coproducts and if f preserves coproducts, then how do you read that? Then f preserves coproducts and g preserves products. Okay. That's interesting, but the paragraph after it, look at it. The special case of the main property of joint pairs, there is a notion of limit and inverse limit, co-limit, which is also called direct limit. If fg is in a joint pair, then f preserves co-limits and g preserves limits. Examples of limits are products, pullbacks, kernels, nested intersections, completions. Examples of co-limits are coproducts, pushouts, co-kernels, and ascending unions. That's,
So a whole new can of worms right there.
man, that's
Adjoints are very deep.
quite a concept.
Another example of an adjoint pair is for all and there exists.
Ooh.
Actually, I think in this order it should be the other way around.
Hmm.
But disjunctions are coproducts in the category of logical propositions whose morphisms are implications.
I should remember this. If somebody asks me for a project, I should just say, explain to me the concept of an adjoint pair.
Good luck.
Keep them busy for a while.
Okay, so now we're getting to, well, I don't think this is super important.
Definition on top of page 333 seems somewhat important.
Yeah, well, I mean, yes. It's used a lot for like the proofs and stuff. Okay. So we have the 1-point compactification. So X is locally compact Hausdorff. Infinity denotes a point outside of X. The 1-point compactification.
I guess the point that I had robbed you of was that the suspension business is just to give a this co-multiplication. It's described in the remark on 332. The co-multiplication on the suspension is obtained by pinching. It's cool.
X, which we call X infinity up here, is X infinity. Code to the topology consisting of all open sets of X together with all sets of the form X minus K union infinity, where K is a compact subset of X. And infinity is the base point of X infinity. Okay, we have certain properties, but I think the most interesting one is that the 1-point compactification of Rn is going to be Sn. That's that's exercise 11.18. So we have
Smash product.
smash. Okay.
Sorry, Nathan. What's going on here?
Okay, and we have different properties of.
The fermionic submanifolds are trying to distract you.
Okay, so we have this smash product. So we have X and Y, then X smash Y. I think that's what you say, right?
Sure.
X cross Y. Mod this product. X wedge Y. Now we get these lemmas. We have that the suspension of X is homomorphic to X smash S1. And X infinity. 1-point compactification of X and 1-point compactification of Y smashed together is equal to X cross Y, but the 1-point compactification of that. Which allows us to prove that the suspension of the sphere, of the n sphere, is homomorphic to the n+1 sphere, because suspension of Sn is equal to, it's homomorphic to, I guess I'll just say equal, okay, it's equal to Sn smashed with S1.
The lemma 11.15 is just, it's like so intuitive, but neat. Thing with infinity. So what's the, lost track of the notation here. What was the sum?
Suspension.
Yes.
Oh, it's a suspension. So the suspension of the n sphere.
What? What are you asking?
This is, I'm just thinking the notation. So some sigma as Sn is a suspension of the n sphere. Okay. Which, in our notation for suspension, what's the, how do you get to the Sn? Which,
Oh, that's lemma
Lemma.
14.
okay,
This is local
okay.
Telstor, then we have that.
Hmm.
And therefore, since each sphere is a suspension, then Sn is a cogroup object for each top star for n greater than or equal to 1. Alright, and now we're finally getting to what we were waiting for.
So excited.
So the suspension is kind of a abstraction of the cone construction.
Yeah.
So suspending the circle. Suspending Sn is the same as smashing a circle onto it. Huh?
Yep.
That's wacky. This is some wacky nonsense.
Yep.
Love this language.
So on the n sphere,
Did I ever tell you guys about the moose calculus?
No.
It's a thing.
moves calculus.
Yeah.
There's the Kirby calculus.
The Kirby calculus. Oh no.
Named after a person or
Named after a
thing?
person.
Oh man.
You're hoping for
I got
that.
excited.
Hope for the game. My daughter plays that on your, was it the little Nintendo DS, and you got her a ancient Nintendo DS for cheap, a bunch of games.
Ancient.
Yeah.
I remember that. Okay, that's so we have pi n of x, x is going to be equal to a set of functions from Sn, Sn into x, x.
Ah.
Like I had mentioned before. Okay, and these are called, when n is greater than or equal to 2, they're called higher homotopy groups. And pi n is a functor on each substar.
So that's a fancy notation for saying what? What's that mean? What is the nth homotopy group of X? I mean, something about maps of spheres?
It's all the, let's see.
What is, I mean, what does the bracket notation mean, I guess is my stupid question.
Yeah, it's kind of like the different families of maps of spheres.
It's the path class.
Or yeah,
Right.
yeah, but like, I guess not really paths anymore.
Yeah. It's kind of like